All right, in this video, we're going to talk a little bit about exchange and correlation holes. I know you've read this in Koch and Holthaus, and my hope is I can give you a little different perspective that makes it somewhat more physical. But of course, the aim is that when we meet in help sessions, you're welcome to ask questions, and I'll see if I can help. On a PowerPoint here, I'm going to use some equations that you've seen in Koch and Holthaus, and then I'm going to switch to a handwritten PDF that tries to illuminate a little bit. So here's the electron-electron repulsion. It's got two terms. It's got the density times the density over R12. So you could think about that. If those densities were not the same density, you have one here that's independent of this, that's exactly how you'd calculate the classical electron repulsion. But this is the repulsion of the total electron density with itself. And we're going to see in a little bit, there are pieces of that that need to be removed and fixed. And they are removed and fixed by this term, which is the density again, times the exchange correlation hole. And its job is to subtract out all the bad things from this. So that's heavy. You see that it depends on R1. So if you tell me where electron 1 is, then that's a piece of this. But it also depends on electron 2, where it is. And the hole, this exchange correlation hole, depends on both those coordinates. That is, you could think about electron 2 as a reference electron, and I'm thinking about R1 moving around, and the hole, its shape changes with that. And so this is a greater overall space. The exchange correlation hole has we break it up to have an exchange part, which only depends on interactions between like spin electrons, and a correlation part that depends on the interaction of all electrons. And it depends again on positions 1 and 2. Easiest way to see what correlation is this. Take H2, and you know you have 2 electrons in the lowest energy, the sigma G orbital. But if I pull it apart like this, oh, I went beyond the screen. If I pull it apart like this to large distance, then you know that H2 has to dissociate to 1 electron over here and 1 electron over here. It doesn't dissociate to 2 electrons in an orbital that could sometimes be on the same side or here or here. It's 1 and 1. Okay? That's correlation. Somehow we have to tell the density through the exchange correlation hole that when the bond of H2 stretches, it's really got to put 1 electron here and 1 electron here. And that's the challenge. So now I'm going to share another document, and it is right here. So this is on this document, as is the PowerPoint on the website, but I'm just going to use it here. You can get it if you like. So what does HXC have to do? Here are the 3 things it's got to do. You're going to see in a minute that the first part of the electron repulsion has orbitals repelling themselves. So it's got an electron repelling itself. That's wrong. We don't count that in the Hartree-Fock or any exact wave function methods. That's got to be fixed. It's got to take care of exchange of like spin electrons. So ρ1 times ρ2 as a joint probability distribution says, I could tell you where electron 1 is independent of electron 2. But if they have the same spin, they can't be on top of one another. So that's not an independent probability. It's got to fix that. And then it's got to deal with correlation, as we said. So I don't know why I numbered them this way, because I decided to do them in a different order. But here's correlation. Here is the helium atom wave function in Hartree-Fock, the ground state. So it's 1s alpha, 1s beta, 1s beta minus 1s alpha. And if I multiply that out, so I take the absolute value squared of it and integrate over all space, I get 1. But the thing in here, once I take out spins, once I integrate the spin parts, is a joint probability density. It is rho of R1, R2. And when you multiply it all out, you see that it is just the square of electron 1 in the 1s times the square of electron 2 in the 1s. So this is a probability for density, electron 1, probability density for electron 2. So I get a joint probability density here. That's just the product of them. But if you were to think about that, supposing R1 and R2 are the same length, but at different orientations, relative to one another. So I can imagine that R2 and R1 are at 90 degrees, so the electrons are that far apart. Or I could imagine at the same length, R1 and R2, they're essentially at 0 degrees from one another. If you look at this joint probability distribution, it only depends, it's a 1s orbital, it's spherical, only depends on the distance. This joint probability has the same size here as here. But that can't possibly be true. The electrons repel one another. So what we need correlation for is to make one more probable than two. That hole has to know when the electrons are near one another. And that's the correlation piece. Then there's the self-interaction error. That is the repulsion of an electron with itself. We know what the repulsion for this two-electron integral, this two-electron wave function should be. It should just be J1s1s. The electrons repel, electron 1 repels 2, and they're both in a 1s orbital. But if you look at how the first term is calculated, it takes the density times the density divides by R12. There's the density. Absolute value squared of orbital 1, 2. And if this is just the 1s alpha and 1s beta, the density is 2 1s alpha. 1s squared, excuse me. So I multiply that all out. And here I get orbital phi 1 squared times phi 1 squared. This is phi 1 repelling itself. I get a similar term that's phi 2 squared times phi 2. Oops, sorry, it should be squared there. And then I get a similar pair of terms, but I've just lumped them together because the extra electron labeling has no impact on this. It's the repulsion of orbital 1, phi 1 squared, times the repulsion of orbital 2, or times orbital 2, and then I get the repulsion. So I see that the first two terms represent unphysical aspects, an orbital repelling itself, whether it be phi 1 or phi 2. That needs to be fixed by the exchange correlation hole, and it's called the self-interaction error, exactly for this reason. It's orbital 1 interacting with itself. Finally, there's no exchange term in J12, and that means that this has to take care of exchange. The hole has to fix all three of these terms, and that is a huge ask. It is exactly the challenge of density functional theory, and as we do some calculations, we'll see how tough that is. That'll teach me to record on my porch. That was our mailman walking by with great music. It was Bob Dylan tune. I think it was done by Jerry Garcia, but whatever the case. We are now going to share the screen again and come back to the PowerPoint. So what we're saying is this HXC right there has to do a whole bunch of stuff. Do we know anything about it? Here are three things that we know about the Fermi part of the whole, the part that has to do with exchange. It has to integrate out, when I integrate over just particle 2 to -1, it has to subtract an electron from the overall density because electrons don't repel themselves. Second thing that has to happen, and there's a sigma 1 equals sigma 2 missing here, is that when the reference position goes to R1, that is when the R2 and R1 become the same, that this has to subtract out fully the density of the same spin particles. Otherwise, it would allow electrons to be on top of one another. Lastly, Hx is always less than 0. We can prove that. What about the Coulomb hole, the part that has to do with the electrons avoiding one another because they're repelled? It integrates to 0, but it shifts charge. That is, so, and what that means is it shifts charge. That is, it can be positive, it can be negative. It doesn't remove an electron, it shifts them. And there's a cusp when the two electrons go near one another, and that has to do with the form of the potential and also the form of the kinetic energy. Okay, so here's correlation. Here's a way to think about it. Hartree-Fock with pairs of electrons in orbitals, when you try and pull H2 apart, you've always got two electrons in a sigma G, which means half the time there's one electron here and one electron here. A quarter of the time there are two here, and a quarter of the time there are two here. It's like the problem Lindy had for N2 only not as bad because it's only a pair of electrons. So the first thing it does is it dissociates improperly. But the second thing it does is its energy is too high here, because even when H2 is at its equilibrium bond length, the fact that the electrons don't stay out of each other's way, raises the energy compared to the exact wave function. You'll notice here that the RHF equilibrium geometry is shorter than the exact. And the way we understand that is it's got a component of the wave function that has to dissociate high. And so it's as if it pulls up what would be the exact term to rise rapidly. So it's like you had a little weight down here and you pulled up on this string, it'd move in like that. Lastly, because of that rapid rise, the curvature here is too large, the vibrational frequency is too large. So here, Koch and Holthausen show you something about the holes. Here's the Fermi hole or exchange hole. Here's the Coulomb hole. All I want you to do is focus on the total hole. So here's my reference electron right there. And what this is showing you is how HXC behaves when bond length is this and the reference electron is here. And you see it digs out charge near the reference electron, but a little bit near the other nucleus because they're kind of close. As you pull the nuclei apart, you see that it digs out more charge around the right nucleus because that's where the reference is basically located, and less around the left nucleus. But by the time you've pulled it apart, even at 2.6 angstroms, the hole is fully on the left nucleus, which means it's dug out all the charge associated with this electron and left the charge that's on this side. You just don't see it because it's showing you the hole. If you want to talk about the Fermi and Coulomb holes separately, I'd love to, but I have a sense this will get super long if I do. So I'm going to stop there and hope for some questions.